Hi, this is Ana Doblas with the second video of the module Electromagnetic Optics. So in this video we're gonna simplify the Maxwell equation for a monochromatic plane wave. We're gonna define absorption and dispersion as processes that occur when the light travels in a medium. In particular, for absorption, we're gonna introduce the Beer's law and we're gonna apply it to determine how much light has been reduced when transmitted through a medium. And then we're gonna talk about different ways where we can quantify the dispersion. So in class number 17, we were saying that the light is electromagnetic light, and we are defining with the electric and magnetic field that a priori they change with the space and the time. However, when we know that we are working with harmonic functions of the time, that's when we introduce monochromatic wave. So that means that the dependence of the time is gonna be expressed as a complex exponential where W, that's gonna be, sorry about that one, so where W is gonna be our angular frequency we can define as 2 pi our frequency, right? So the moment that we are working with electromagnetic fields, remember that we don't only have our electric and our magnetic field, but for the electric and the magnetic field, we're gonna have the flux density fields. So those two are gonna also be dependent on the space and having the same relationship with respect to the frequency. So we have our four fields: our electric field, our electric density flux, our magnetic field, and our magnetic flux density. And we know that there is a relationship, like these fields are related with each other based on the Maxwell equation, where in a general we have here the relationship or the partial derivative of the electric and the magnetic flux density. But because our system, or because our fields are monochromatic, meaning that they follow a complex exponential in terms with respect with the time, then the curve of the electric and the magnetic field can be simplified. So we can do those partial derivative just pulling out a factor j omega, because the system depends on it's monochromatic with respect to the time. So let's ahora consider that not only our fields are monochromatic, but they are also plane waves. So that means that the component changing with the space can also be, sorry about that, this is going a little slow, but it's also given by a complex exponential. So this is telling me that we have plane wave. So obviously every component of the electric magnetic field, they need to satisfy, in this case, the Helmholtz equation. But now when we are imposing that the fields follow a plane wave where k is the wave number, so let me put it out here, that k right here, this is gonna be a wave number vector, wave number along the propagation of the plane wave. So having into account that the fields are plane wave, so then we can solve the curves of the electric and the magnetic field. so that we know that the wave number, the cross product with the wave number and the magnetic field is gonna give you the electric field, some proportionality of the electric field, but it's parallel to the electric field, and the cross product between the direction of the propagation of the wave number of the light and then the electric field, it's parallel to the magnetic field. So these equations, the relationship of the propagation of the plane wave with respect to the magnetic and the electric field being the other corresponding field, what at the end tell us is that the direction of the propagating beam and then the electric field and the magnetic field, they are mutually orthogonal. So that means that what we are working is with transverse electromagnetic waves. So a lot of time we're gonna find this as TEM, where the T's are transverse electromagnetic wave, just meaning that that all the films with respect to the propagation, it's gonna be perpendicular to each other. If we kind of want to take if we want to draw our attention to the amplitude of the fields, how they are related with the wave number, we know that at the end a wave number, it can be given as the ratio of our angular frequency versus our velocity. This relationship right here, this is based on Module 2, but then when we are writing the velocity, we can say that the refractive index is C over V. So this is already what we study in the first classes of the course, right? So at the end, what we can say is that our wave number, it's the refractive index. So what we are saying here as a magnitude is that wave number of the medium is the refractive index, and then the wave number at vacuum. So this is gonna be wave number at vacuum of free space. Remember that it's always the same. More importantly, these equations, the equations coming from the Maxwell relating to the magnitude, is telling us how the electric and the magnetic amplitudes, they are related to each other in terms of the medium impedance. And again, as always, the medium impedance for the vacuum is gonna be this particular constant. So let's talk. So this is so far what we wanted to revise as what is going on when the Maxwell equations, when we are assuming that we have monochromatic and plane wave. But let's think about what are the effects that light is gonna occur to the light when they passes through a medium, right? So when light passes through a medium, it's gonna experience absorption and dispersion. So absorption is kind of represented here on the left side. So what that means at the end is like you are putting light on the medium, but the light can be absorbed by the medium or can be scattered. And when you are scattering, it's in a different direction from the incident light. And then you're gonna have some light that is gonna be transmitted, right? So absorption is a lot of time taking account about how much light has been transmitted versus the incident about it. The dispersion is related with a reduction of the speed of the light. So when we change the medium, we change the refractive index. So we know that the medium in the air on the vacuum, it's 1, but in a different medium it's gonna be higher. So we have the reduction of the velocity, and that's gonna affect differently when we change the wavelength. So in other words, that picture is what we have always in mind, how we can decompose all the spectrum of the colors coming from white, like just through passing the light through a prism. because now every wavelength or it's gonna be refracted at a different angle. So I want to talk a little more about absorption, and especially I want to make a difference between general and selective absorption, right? So general absorption is that there is the same drop of the intensity regardless of the wavelength, right? So if we are losing 50% of the light, it doesn't matter if the incident light is if green, red, or both of them, right? But selective absorption occurs when the material absorbs some particular wavelength within the input light, and therefore we have some absorption of some wavelength, but then we're gonna have some transmission about it. So I really like a lot this kind of drawing, because what this is kind of telling us how we perceive colors, right? So when we see something that is white, means that if we are illuminating with all the light, all the color, right, all the colors are gonna be reflected. But objects appears with the red color means that only the red color is reflected, so the rest of the wavelengths are gonna be absorbed by the system. And we can do the same example when we observe an object with the black color, means that all the incident light coming is gonna be absorbing. So selective absorption, it's a lot of time related with what is the appearance of the colors, because the other ones are gonna be absorbed with it. So when we describe the absorption, we need to always think about how much light has been reduced when traveling through a medium, right? So we know that we have a medium where you're gonna have kind of like a thickness or light is gonna travel at distance x, and the Beer's law is gonna tell us how much light. So remember that this is the Beer's law, and it's telling us how much light is transferred through the medium. So we need the input light, we need the distance, but then we need alpha. And alpha is the linear attenuation coefficient, and alpha is gonna depend on the medium and the type of medium that we are, right? So we can from the attenuation, or sometimes we call it absorption coefficient. So we can define the penetration depth as the inverse of the attenuation or absorption coefficient, which is gonna be the distance in which the drop of the intensity has been reduced by a factor of 1/A. So let's kind of practice a little bit the Beer's law, right? So we have a certain medium that we know that transmits 80% of the incident light, and it's gonna get traveled through a medium that is gonna have a distance of 50 meters. And we want to estimate the absorption coefficient, right? So this is telling us that we have here our input, that we have a medium that we don't know what is gonna be the absorption coefficient, but we know that travels 50 meters, and at the output, the transmitted light is 80% the incident one, right? So if we want to apply the Beer's law, and we need to find alpha. Alpha is what the problem is asking us. So we do the ratio of the intensities, it's equal to the exponential of minus A alpha. So the natural logarithm of the intensities is minus alpha x. That minus, I can make alpha as we change the order of the intensity, and then because we have the x, we're gonna divide by x, right? And now, if we plug our value, right? If we say that x is equal 50 meters, and the final intensity is 0.8, the original one, then so we're gonna have here the natural logarithmic of I0, 0.8 I0. So as you see, the initial input cannot cancel each other, so it's not important for solving the problem. As far as the transmitted input, it's given based on the original input. So we have that this is going to be 4.463 multiplied by 10 power minus 3 meters and minus 1. So remember, alpha unit should be the same as x unit, and always it's gonna be meter inverse of meters. Sometimes we want to express as an inverse of centimeter, but it's always a distance, so it needs to be on meters. So when we were defining the selective absorption, so I guess that you guys are gonna thinking what is gonna change for the Beer's law. So what is gonna change on the Beer's law is now when we have selective now absorption here, what it means is that our attenuation coefficient is wavelength dependent. Therefore, our transmitted intensity is gonna be also wavelength dependent. A lot of time we don't want to talk about how much light is transmitted. We want to talk more about the medium transmittance, which is just the ratio of the transmitted light versus the input. Or sometimes we also find the medium absorbance, where the medium absorbance is just the log. This log is gonna be the natural log of the inverse of the transmittance. So in general, in our medium, we might not only have absorption, we might also have a scattering. So this, we're gonna have two coefficients. We're gonna have the absorption coefficient, but then the scattering coefficient, that's gonna be about thinking that we have particles in a medium that is gonna disperse the light in a different direction with respect to the incident light. And then that's just how we're gonna change the Beer's law when we have both. We have absorption and scattering. In the video of the multi-choice questions, we're gonna solve a problem where in the medium we have both. We have absorption and scattering. So in general, we were saying in class 17 that we can write our refractive index in terms of the electric and magnetic properties, right? And in general, if the medium is not magnetic, meaning that the magnetic permeability is the same in the medium or in the vacuum, the refractive index is just the ratio between the electric permittivity in the medium versus the vacuum, and that could be expressed as 1 plus the susceptibility square root if we were having the medium here, that the medium was to be linear, homogeneous, non-dispersive, and isotropic, right? So we can write all of that. In general, in this class, what we're gonna introduce is that our refractive index, it can be complex. So that means that our susceptibility is complex, as well as wave number is gonna be also complex, right? So we know that we have a plane wave. Let's assume that they have a plane wave traveling along the z direction. So now this is gonna be my complex wave number, right? And when I'm decomposing every term, I find out that the absorption coefficient, this is gonna be a change of the reduction of the amplitude, which if the alpha value is positive, it's a reduction, so it's what we are getting from the Beer's law, versus if the alpha is negative, the medium amplify the light, and that's the mediums that we have inside the lasers. On the other side, the imaginary part for the plane wave, which is going to be the real part of the wave number, this is related with a change in the propagation of the plane wave, right? This is going to be related with the phase velocity and the reduction when we are changing mediums because the increase of the refractive index. But overall, where it's important in this class is kind of identifying that we have in general a complex refractive index, where the real part of the refractive index is going to be with the phase velocity. The imaginary part is going to be related with the extinction coefficient, or the amount of the attenuation. And at the end, we're going to see that the real and the imaginary components, they're going to be related through the Krebs-Kronig relations. All right, so let's talk a little more about dispersion, right? So dispersion, we were saying that is the light with different colors or different wavelengths travel at a different speed. So this is just kind of saying that our refractive index changes with the wavelength. So our refractive index change with the wavelength is the susceptibility and the electric permittivity. It's also wavelength dependent. And here we have like some plots of real materials and how they change with the wavelength. So at the end, what it's gonna see, like we were introducing the real case when we have the decomposition of the light. So, but kind of like, and I'm gonna talk a little more after, but we define the normal dispersion. Sorry about my handwriting. So we're gonna define normal dispersion as the refractive index reduces if the wavelength increases. So I want you to think about the Snell law, right? So let's assume that we have here air, and this is our prism, which is gonna be glass, right? And here, at this particular surface, we need to satisfy the Snell law, right? So here we need to satisfy the Snell law. So it's telling us that the refractive index of the air, sine of the incident angle, needs to be equal to the refractive index of the glass, sine of the different angle, of the refracted angle, right? But we know that the wavelength, we know here that the wavelength, the refractive index changes with the wavelength, right? And we are saying that if the glass represents glass normal dispersion, which it does, the refractive index is going to be less when we increase. So what this means is that if N2 reduces for the wavelength, right, that means the angle needs to increase. So because at the end, everything needs to be constant. So the refracted angle is going to increase if the wavelength increases. And that's why we see such a decomposition when light travels within a medium. So how we can measure the dispersion, how we can measure that speed delay of the light in a medium versus the wavelength. So there are three different parameters. The first one is the Abbe number, which is denoted as capital B, and it's just we need to provide the refractive index at three different wavelengths and do the equation, and then the wave number is already well known for a lot of materials. It's already well calibrated, and basically low dispersion, it's gonna be reflected with high numbers of the Abbe number. The other way to, or the other parameter or approach to quantify the dispersion is gonna be the Cauchy equation. So the Cauchy equation kind of express the refractive index in terms of the wavelength, and for every material we need to identify the constants A, B, and C that usually are well calibrated and they are always in a table. And this is like a representation of the Cauchy versus the Sellmeier, or like the measure one. So we see that every time that we are in the visible range, so from 100 to 700, the Cauchy equation is really accurate to measure the wavelength. However, it's only accurate if the medium follows normal dispersion. So that means that the material should not have absorption in the visible range. Outside the visible range, it's better if we use the Sellmeier equation of even if the medium has absorption. So for the Sellmeier equation means that it's a little more complex. So we have 1 plus and then fractions of a constant A, and then we define also a resonant wavelength square. So, and we can have as many resonant wavelength as kind of like absorption bands the medium presents. Definitely in the visible range, if the medium has normal dispersion, the agreement between the Cauchy and the Sellmeier is really good. But as far as the wavelength increases, then the Cauchy gets less accurate, and it's more accurate the Sellmeier approach or the Sellmeier equation. So if we analyze and if we plot the Sellmeier equation, what we're gonna see is that every time that the wavelength approaches a resonant wavelength, the refractive index is gonna divert, and this is kind of telling us here that here what we're gonna have is an absorption band. And the same here, like every time that we're gonna have it, that means that we have an absorption band. When the refractive index is gonna be equal to 1 if the wavelength is equal to 0, which is gonna be kind of like one extreme scenario, and then otherwise we're gonna have, it's gonna convert for a really huge number of the wavelength. So the reason that we have this resonant wavelength is because we are considering that the particles in the medium, they are bounded with electric forces, and they are able to vibrate at a particular frequency. So those are frequencies, or those wavelengths corresponds to the frequency in which the resonant frequencies of the particles bounded on the material. So I want to think like this kind of vibration when we have like this image of the bridge, that it was kind of really moving as a wave. So those are gonna be the frequencies here where the particles in our medium is gonna move as the bridge, because we are hitting the wavelength that we are illuminating is exactly the wavelength, the resonant wavelength. So just to finalize this class, which I need to apologize because it's a little long, but I'm just gonna want to do the last in-class problem, where what we have is the Sellmeier equation for the BK7 glass. It's a really common glass made by a lot of optical components. We need to say how many resonances the medium has and what is gonna be the resonant wavelength. So because we have 3 terms, right? So we're gonna have 3 resonant ones. The first one, and remember that was a square, so the first one is gonna be a 6.0007 power minus 3. So that's gonna be 0.0775 microns. The second one is the square root of 2.0018. so 0.14148 microns, and the last reasonable wavelength is the square root of 1.0356, and that is gonna occur at 100,176 microns. So that's gonna be a really long wavelength. So I hope that you enjoy today's class, and next module it's about polarization optics. See you soon.